Okay, so I was going to speak about today some new experimental avenues involving the use of X-ray free electron lasers to investigate coherent nuclear dynamics involving biological cofactors. So this work involves a multidisciplinary team from our group at the University of Arizona, also Arizona State University, University at Buffalo, and University of Rochester, and of course SLAC National Laboratory, where the work is actually carried out. So I have to say that quantum biology is very popular in Arizona. We have lots of quantum biology, and we also have entangled states. So here's a couple examples right here. So you can consider this to be a biological example of the quantum entanglement that we've heard already. So what I'm going to speak about then is going to be the use of ultra-fast X-ray free electron lasers in quantum biology. I'll say a few words about protein dynamics involving coherent nuclear and electronic motions. And that'll lead us to the example of rhodopsin, where cis-trans isomerization is driven by the electron dynamics. And then we'll finish up with a few words on protein quakes and how nuclear motions, coherent nuclear motions, are involved in the energy landscape. So the fundamental question that's being investigated here involves how the non-adiabatic electron dynamics that are associated with cis-trans isomerization of retinal and rhodopsin are coupled to the coherent nuclear dynamics that leads to visual signaling. And so the way we're investigating this is as follows. So we're interested in how the ultra-fast structural methods involving free electron lasers can inform the electronic and the nuclear wave functions, and that's going to lead us well beyond the Born-Oppenheimer approximation. So it's inherently non-adiabatic quantum molecular dynamics. And so how are the coherent nuclear motions, electronic motions, propagated into the nuclear motions, which give rise to chemical reactivity? And ultimately, we're interested in the quantum mechanical basis for the ultra-fast cis-trans isomerization of biological chromophores, where retinal is a prominent example. So to investigate these questions, we're using X-ray free electron lasers. And the impact of X-ray free electron lasers in quantum biology is that we can reach the quantum limits both in space, meaning the angstrom level, and in time, meaning approaching the femtosecond level. And actually, we'll go beyond femtoseconds with LCLS2. So we have a very brilliant X-ray flux, which is about 10 to the fold greater than synchrotron rings. And so at LCLS, at SLAC National Laboratory, currently one can produce 10 femtosecond pulses with 120 hertz repetition rate. And on the horizon is LCLS2, where the repetition rates are going to be megahertz, and possibly we'll get below femtoseconds into the attosecond regime. So this is going to open up new dimensions of how we can experimentally approach problems in quantum biology. So just a little bit of an overview here. So at LCLS, which is line-at coherent light source, one has an electron gun and basically a linear accelerator, which generates bunched electrons, which lead to emission of X-rays, which then are subject to an undulator, which leads to further electron bunching and basically an X-ray lasing effect, which can be thought of in the following way. So in the undulators, one has an electron bunch. The magnetic undulators lead to emission of X-ray photons by electrons. And so the resonant interaction of the electron bunches within the undulators lead to periodic structures. And the electron bunches radiate coherently in phase to produce laser emission. And so with this, one can get to 10 femtosecond pulses in synchrotron rings. Due to the structure of the ring, the limit is going to be about 100 picoseconds. So it opens up a new dimension of time and space in quantum biology. So this is the undulator hall at LCLS, just to give you an idea of what's involved here. And this is in the tunnel before the experimental stations. So it's all deep underground here. So you enter, go underground, and here's our experimental team actually involved in these sorts of experiments here. This is probably the night shift. You can see we're all happy as usual, and this gives you an idea of some of the experimental parameters. So this is a very good day at LCLS. It doesn't always look this way, but if you see this, you're happy, very happy. And so this is the 120 hertz repetition rate. The X-rays are going to be at about 9.5 electron volts. The wavelength is going to be 1.4 angstroms, and the repetition rate is going to be 120 hertz. So the experiment then involves taking the intersection of the pump laser with the X-ray beam, and the sample is contained in a rapidly flowing jet, which is contained in a gas dynamic virtual nozzle. And so one basically has to have the intersection of the sample jet, the LCLS beam, which is the probe, and the pump coming from an optical parametric amplifier. And these are examples of some of the results that we've obtained. So the idea is that we can obtain basically femtosecond, or we're approaching femtosecond X-ray scattering of visual proteins. So these are data obtained at LCLS for visual rhodopsin. These are pump probe experiments involving coherent nuclear motions, which are stimulated by coherent electronic motions, which involve the earliest events in visual excitation. So one sees coherent oscillations in the light minus dark, different scattering profiles. And to interpret these data, ultimately one is going to need non-adiabatic quantum simulations. So these are our results for rhodopsin at LCLS with two different pump probe delays, 10 picoseconds and 100 picoseconds. And these are also data obtained in Japan at Saka, with an even shorter delay of about 2.6 picoseconds. And I'll come back to the interpretation of these oscillations momentarily. Okay, so I'd now like to turn to protein dynamics and the issue of coherent nuclear and electronic motions. And so the work that we've done involving rhodopsin is paralleled by studies of a globular protein, which is myoglobin, which we can consider to be the hydrogen atom of biology. So myoglobin is an aqueous solution with a hydration shell, and its dynamics are described by a hierarchical energy landscape as most prominently put forth by Hans Frauenfelder. And so here are now pump probe studies of myoglobin carried out not by our group, but by the group of Camarada in France. And so one can observe the wide-angle scattering regime and the small-angle scattering regime defined by the Q space. And what one sees in the wide-angle scattering as a function of the pump probe delays is the appearance of oscillations in Q space, which appear and disappear in a coherent way that I'll talk about in just a moment. The wide-angle scattering then is approaching the very short dimensions characteristic of the functional groups in the protein. In the small-angle X-ray scattering regime in the Guinea region, then one can probe the radius of gyration and also the volumetric fluctuations of the protein. So the way these data are interpreted is as follows. So in the SAX regime, one can monitor the light minus dark change in the gyration radius and the corresponding change in volume. What one sees is a lag first, and secondly, oscillatory behavior on the picosecond timescale. And so it appears as if the initial structural collapse of the protein then involves shorter atomic distances, which then are manifested by the subsequent volumetric expansion of the protein. But the key feature here is going to be the oscillatory behavior. And the oscillatory behavior is not what one expects for overdamped global protein dynamics. And so the thinking goes in this paper is that the elementary motions at the level of a single protein have a quake-like ballistic nature after an ultra-fast perturbation, and one sees coherent oscillations which are lost in the ensemble average due to interference effects among all the incoherent members of the ensemble. So one has underdamped vibrational modes which involve the heme, the F helix, to which the heme is covalently bound, and the other helices of the heme. But the idea of underdamped oscillations is inconsistent with basically everything we know about overdamped global protein dynamics. So the question is, are they real or not? So in parallel, we've been investigating rhodopsin. And so in the case of rhodopsin, one has cis-to-trans isomerization involving nuclear motions which are driven by the coherent electron dynamics. And so in the case of rhodopsin, the chromophore is retinal, which is derived from vitamin A. It's what we're all using to see with as we speak. And so the retinal is deeply embedded in the protein, which comprise 7 transmembrane helices embedded in a lipid bilayer, so it's a membrane protein. It's a class of proteins. It's the archetype for a class of proteins which are called G-protein coupled receptors, GPCRs. And so one has a chromophore which interacts with the protein, which interacts with the lipid bilayer, which is embedded in an aqueous medium. And so the fundamental event of vision then is going to be the cis-to-trans isomerization of retinal, again derived from the vitamin A that we all have in our diets. And so the initial event is going to be then generation of an excited state, which then leads to cis-trans isomerization, yielding photorhodopsin, beta-rhodopsin, and a series of subsequent thermal relaxations that I'll talk about at some other time. So the work I'm going to talk about is focused on the initial events of visual excitation. So to summarize, photoactivation isomerizes retinal to all trans one has an equilibrium ultimately set up between states on the millisecond timescale that lead to visual signaling. And so X-ray structures are available, putative X-ray structures are available for the light-activated state and the dark-activated state. And the key observation is that helix H6 and H5 pair together and separate from the H1 to H4 helical bundle. So that's the basic knowledge that's obtained from X-ray crystallography. So in terms of spectroscopy, the initial event in visual excitation involves the isomerization of retinal. It's very fast. This is the work of Mattis et al. At Berkeley. It occurs within 200 femtoseconds, and so the 11-cis retinal is pre-twisted in the direction of the torsional isomerization. And due to steric interactions, basically one has a bicycle pedal mechanism where the 11-12 double bond is isomerizing concertedly with the 9-10 double bond, but the 9-10 isomerization is aborted, and one is left with the 11-12 double bond isomerization. And so what one has then is an excited state in the vertical, which is populated by the vertical Franck-Condon excitation. And the ultra-fast electron dynamics are going to be inherently non-adiabatic. And the original interpretation was avoided crossing, but now it appears that it's a conical intersection between the excited state and the ground state potential surface as a function of the nuclear coordinates. But still, this is ultimately resting upon ideas of adiabaticity in the sense that the very notion of a potential energy surface is somehow going to be connected then to the Born-Oppenheimer approximation or diabatic extensions thereof. So in this experiment, again, this is the work of Rich Mattis at Berkeley. This is a transient absorption measurement. And what one sees then are quantum effects in the transient absorption spectrum as a function of a pump-probe delay. So one populates the excited state, and then one probes the excited state with electronic spectroscopy. And what one sees then is a transient rise in absorption due to the photorhodopsin and perhaps beta-rhodopsin intermediate states, coupled then to, I'll say, oscillations, coherences, vibrational coherences, which can be Fourier transformed to give rise to the vibrational period, which is about a half a picosecond. So that's what's known from electronic spectroscopy. But you know, we really need to start looking at the nuclear coherences as well and how they're driven by the electronic coherences. So we can't apply Heisenberg to everything. Let's do some experiments. So now these are the realities of how you can probe the corresponding structural changes on ultra-fast timescales. So here's the 1.6 kilometer long free electron laser beam at LCLS. These are some of the individuals involved in the experiment. And so what we're doing is loading the sample. This is Rick Kurian from Arizona State University, loading the sample then into the beam. And so we need to get the beam loaded with the sample. And so this is perhaps inspired by Michelangelo, if you wish. And so here's the sample, and this is Rick Kurian, not God, which is almost the same thing, actually, which is then going into the electron laser beam. And this is what the free electron laser beam. And so here now is what the experiment actually looks like. So this is a very thin gas dynamic virtual nozzle focused jet. So it's focused to about 4 micron diameter. And what you're seeing now is the much larger pump laser beam photo-exciting the rhodopsin molecules. Here's another view of the free electron laser beam being intersected with the pump laser. So the actual sample that we investigate is now rhodopsin, which is solubilized in detergent micelles. And one of the game-changing aspects was to use a detergent called CHAPS, which has a very low aggregation number and forms, if you wish, a belt or a waist about the membrane protein, which is inherently soluble in a lipid bilayer. And so, again, rhodopsin has 7 transmembrane helices, and it's embedded or solubilized in a detergent micelle. And that then is supplied as a jet by the nozzle in the X-ray free electron laser experiment. Okay, so I have to tell you a few dirty little secrets now. So X-ray free electron laser time is very valuable, and so you're lucky to get a few shifts a year. And so control experiments are not really done in free electron lasers, but there's a number of controls that one has to do. The first is one needs to correct for the detergent background, and that's relatively straightforward. So this is now a rhodopsin solubilized in CHAPS detergent, and so we need to do the detergent buffer controls and subtract that in a way that I won't go into to obtain the oscillations now that correspond to the light minus dark different signals of rhodopsin as a function of Q space. But the question is, how much of this is due to the excess energy of the free electron, of the pump laser, introducing oscillations in the protein versus the actual electron dynamics due to light absorption by the retinal chromophore. And the other experiments that I showed you involving myoglobin have not been done with the appropriate control, which involves apomyoglobin, which is taking away the chromophore and seeing what the actual effect of the light absorption is. And that's because it's very expensive to produce apomyoglobin, but we're probably going to do this anyway. Other experiments involving reaction centers likewise are compromised by the inability to remove the chromophore. But in the case of rhodopsin, one can produce the apoprotein, opsin, as well as rhodopsin, which contains the retinal chromophore. And so these are double difference experiments done by the analysis done by Derek Mendez. And so the double difference then involves the light minus dark experiment involving rhodopsin, and then one has to subtract the light minus dark result for the apoprotein opsin, and in the double difference now, is where we see the actual retinal-specific signals in Q space, which then evolve with time. And now the question is, are these oscillatory, or are they involving a growth without any oscillations, as we might expect from what we know about ensemble average protein dynamics? And so these are the results as of about 2 days ago. So that's what Derek spent his Thanksgiving holiday doing, which is analyzing these data for this talk. And so this is going from, I'll call this 0, call this time 0 if you wish, all the way up to 10 picoseconds. And these are the double difference experiments, rhodopsin minus opsin. And so now what one sees is the appearance of different signals, which can be subject to singular value decomposition, and that's what the signal looks like. And here's the growth. So we don't see oscillations in these experiments, which is perhaps what one might expect. So to summarize at this point, on the 0 to 10 picosecond time scale, we can observe the structural correlates involving coherent nuclear motions, coherent nuclear dynamics, which are non-adiabatically coupled to the electron dynamics that are studied with very rapid timescales, but with much lower spatial resolution in the case of electronic spectroscopy. So now I'll say a little bit about protein quakes, and I guess I better speed up a little bit. So one approach is to use classical molecular dynamics simulations to explore how the coherent isomerization of retinal ends up as the large-scale protein motions in visual excitation. And so that's done in silico by adding, by basically changing the potential of the 11-12 double bond and forcing the isomerization. And if you do this, then one can calculate the center of mass of the various protein residues relative to the retinal chromophore, and what one sees is a gradual spreading out over a time scale of picoseconds from the initial site of the trans-gauche isomerization to the rest of the protein. And so this is what we will call a protein quake. And if you plot the distance from retinal as a function of time, what you'll find is it gradually spreads out. And in fact, you can sort the protein residues by their distance from retinal. And what you find is that there's a propagation of the light-induced perturbation as a pressure wave, which matches the speed of sound in proteins. And so you can go and calculate the radius of gyration as a function of time. Now, in the case of LCLS, in addition to the wide-angle scattering, we can look at the small-angle scattering. And the small-angle scattering is the large distances, which are going to be related then to the large-scale protein changes. And here, too, we see the growth and the decay of negative and positive difference signals, where we think the loss of coherence is ultimately going to be associated with the transfer or the propagation of the excitation across the protein via the hydration layer to the bulk solvent. So this is the change in the radius of gyration, and this is the volumetric change as a function of time in the wax region, where we can obtain in the Guinea analysis then the large-scale changes. And so what we see again is a lag between the radius of gyration. We think that the protein, after isomerization, there's a localized collapse because the retinal is isomerizing, and then that ultimately is ending up as a volumetric change as a function of time with an oscillatory behavior, which ultimately is damped, again, due to propagation to the bulk solvent. So just to wrap things up at this point, so we'll say that pump probe studies of photoactive proteins, such as rhodopsin, can investigate the coupling of the electron and the nuclear dynamics, that the ultrafast cis-trans isomerization of retinal shows how the nuclei react to the electronic motions, And so the protein quake, ultimately at the quantum mechanical level, ends up as large-scale protein changes. And so where this is heading is to go shorter in time and longer in time. Shorter in time with LCLS2, but we'll have to wait a year for LCLS2. And in that case, we'll get down below femtoseconds, maybe into attoseconds, where we really approach the structural changes that correspond to the electron dynamics. But ultimately, these end up as the large-scale changes in visual physiology, which occur on milliseconds. And so it's an inherently multi-scale mechanism that we need to probe. So where we go from here, I'll say that rhodopsin is certainly going to occupy us for quite a while. In terms of the ultrafast structural arrangements and spectral tuning, there's a related protein involved in energy conservation, which is called proteorhodopsin. And this is also a subject of great interest because it's competitive with chlorophyll-based photosynthesis. And ultimately, at the quantum level, we need to focus on multi-scale dynamics and also the quantum mechanical non-adiabatic simulations of cofactors in biological systems. And so I'll finish up by acknowledging some of the key members of the group, Petra Froma and Rick Kurian and Nadia Zatsepin at Arizona State, and also Tom Grant at Buffalo and Alan Grossfield at University of Rochester. And with that, I thank you very much for your attention.
We have some questions.
I have a couple questions. So what's the current belief on the 200 wave number under the bold myoglobin? Do you believe it exists? And then I have another follow-up on the rhodopsin.
I believe that it involves the hydration layer, the so-called beta fluctuations of yourself and Hans Frauenfelder and colleagues, which are propagated into the bulk solvent and the alpha fluctuations of the bulk solvent. So it ultimately is going to involve the transfer of the excitation, which is propagated within the protein by a pressure wave, basically, non-oscillatory, but ends up ultimately in the solvent. That's what I believe, but it's subject to further experimental test.
That's an interesting one, if we can get this. On the rhodopsin, you talk about quantum mechanics, and I agree that there is normalization is quantum mechanics, but after the energy is dumped and you have the protein quake, can I just treat that classically? Why you say it's quantum, or not, basically? The coupling between the transition and the protein has to be treated quantum mechanics, but after that, is that propagation of the quantum quake?
So presently, we're restricted to longer, relatively long timescales, what's called picoseconds, because we have 10 or 20 femtosecond pulses with LCLS. But ultimately, we're going to be able to have sub-femtosecond pulses in the attosecond regime. And at that point, then we can start probing the actual nuclear or atomic motions, which are directly coupled to the electronic motions that are investigated in electronic spectroscopy. So we looked very hard for oscillations. And as of right now, we don't see them. But it may be due to the ensemble averaging, the decoherences that manifest themselves in practical experimental terms, if you wish. That's what I can say at the present time. So to summarize, within the protein, we think it's a pressure wave. But that's the local changes within the protein. But the larger scale changes do seem to have some oscillatory behavior. And that seems to end up or dissipated, if you wish, damped by coupling to the hydration layer and ultimately to the bulk solvent.
Interesting. So Carlos Bustamante did an experiment where he used the heat of reaction in an enzyme. These are single molecule experiments, and then looked at the impact on the movement, the diffusion of the protein. And he concluded, this was published a couple years ago, I think in Nature, he concluded that there was a directed release through the protein of the heat evolved in the net reaction. And so I'm wondering what you're in this case, do you think it's isotropic, the way the heat is distributed, or do you think that there are specific funnels, if you will, or structures within the protein that are leading to this mixing of the heat in the inner and outer sphere water molecules?
I think it's anisotropic, and ultimately it's heat and work. And so the displacements, if you wish, are most likely, and of course this is what one would like to know, how are they reflected and how do they migrate throughout the protein to go from the retinal, which is deeply embedded in the protein, to what I believe are large-scale activating fluctuations involving the transmembrane helices, which are associated with the catalytic activation of the G protein transducin. So I'll just say that I believe it's anisotropic.
In myoglobin, not I think so much in rhodopsin, but in myoglobin, because there's no reason functionally to have it be anisotropic. I think here the protein needs to respond in a particular way to the isomerization. But just could you look at myoglobin even and see?
Okay, the person who's done probably the most significant theoretical work interpreting these free electron laser measurements is Joachim Hub at the University of Saarland in Germany. And he believes that it's anisotropic in myoglobin, and that I'm not a myoglobin expert, but there's some doming of the iron out of the heme plane, which is
then directly related to a subsection of the protein.
Yes. And then, that does lead to oscillations, which end up in the solvent. So he believes it's anisotropic, and ultimately, I would have to say that makes a lot of sense.
But there's no way currently to look at a protein and try to predict which region would be most susceptible to this. As far as I understand, maybe you could comment on that, because I think that would be very relevant to this heat transduction from the outside to the inside that has to happen during catalytic turnover.
Yes. Well, I mean, ultimately one has coherences which end up as incoherent motion, which is, in a thermodynamic sense, one does work which, in some heat engine sort of way ends up as heat. And so, one has directed motion, which is ultimately going to be dissipated in some way. So at some level, it has to be directed and has to be anisotropic. But ultimately, it's going to be anisotropic when it's dissipated as incoherent, heat-like motions. I mean, that's a thermodynamic argument of something that's inherently quantum. But
I think we're asking somewhat different questions, but we can talk about it.
okay.
So I think it's necessary for me to comment once again on what I mentioned yesterday with respect to this retinal, these experiments, which applies to all of these experiments, and that is that this is what these experiments reveal: enormous information, detailed information about the nature of the Hamiltonian, the system-bath couplings, and so on. But this is not what happens in nature, because nature operates in incoherent light, establishes, in this case, a steady state where there are populations of meta-rhodopsin and metarrhodopsin, and all of the rhodopsins along the way towards the transduction path. So we have to be very careful about answering questions like, is the heat generated isotropically or so on? You're asking a question about a specific experiment, and that experiment may not tell you what actually is going on in nature.
Fair enough. I mean, these are in vitro systems, and it's probing, the behavior of individual rhodopsin molecules, which are removed from the membrane in a detergent environment. And to the extent that one can infer the behavior in vitro is open to discussion. I mean, these are all very fascinating topics. I mean, we're talking about an inherently multi-scale process, and there's a lot that happens after the initial photophysics.
But not, again, I want to point out that the photophysics is different in nature than it is in these experiments. Here you're using pulsed laser sources, you're using X-ray sources, you're even talking about going to attosecond sources. Each one of those steps is going further and further away from the natural process to reveal detailed information about the system. And this has to be taken, from my perspective, back into the incoherent excitation by using results obtained in these experiments to then either model or experimentally look at the incoherent excitation. That's what I'm trying to say.
Yes, fair enough.
Okay, any last questions? Well, with that, I think we'll take a short break. Coming back.